All right, so now the goal for the rest of the day is to do that same thing, but do it at the same time as the simulation is running. So why do we even want to do streaming I/O? If we look at the recent big compute systems, for example, these are the ones at Oak Ridge, from Titan to Frontier, you see that the I/O performance as well as the compute performance both are growing, but they are growing at different rates. So there's a gap, and that gap is widening. And the I/O system at Frontier, I really have to say, is good. It works really well. It has good performance, and it's really a usable thing. But still, the gap is going up, and we are reaching the limits of the file system at fractions of the entire system size. So the parallel bandwidth is insufficient for HPC at full scale, as well as the actual storage capacity that we have. Yeah, you get the angry emails about deleting your data, please. Same trend we get in a different way, kind of in experiments where we have increasing camera resolutions and data rates. And this is important for us because a typical scientific workflow is going to exchange data. And when we want to read data in an analysis code from a simulation that outputs massive amounts of data, and pick on GPU is an example for that because it is memory bound, then at some point we get a problem by having to go through the parallel file system and are limited in our scalability, not from the actual codes, but from the limited resources that we have in order to connect these codes together and to make them communicate. So the idea is to do streaming instead. It's of course not a free lunch solution. Again, there are other challenges that come up. For example, in how do I exchange data? What are the data exchange patterns? I cannot random access data any longer, but I only see the data that is currently coming. But these are, for example, results that we had on Summit, so the last gen system at Oak Ridge, where the green and the yellow line, you don't need to care now about the difference between them. They are different configurations for doing file I/O. And we see this little gray horizontal line depicting the parallel file system bandwidth of the system. And we actually reach the bandwidth of the file system at 512 nodes. Summit, if I remember correctly, had around 4,500 nodes, so that's a fraction of the system size. And after that fraction of the system size, I/O didn't scale any longer. And this is actually a very good I/O result still, because it actually shows that with ADOS we were able to get close to what the system can give us. But of course, even the best code cannot do witchcraft and go beyond what is possible. But with doing streaming I/O, we were able to get output out of the system at a higher data rate than what theoretically the parallel file system could give us. Now, you could say it's kind of obvious that we are not affected by this capacity, but it's still the thing that we are competing against. It's important to show that we are actually getting better than what this capacity is giving us. Now, if you look at the green line here, we are seeing a different representation for that green line on this slide, where we have on the left-hand side the time that I/O writing takes. And you see that we have at 64 nodes around 10 to 15 seconds. This number is somewhat going up. There are more and more outliers as we go higher. And like I said, at 512 nodes, there was the point where we reached the file system capacity. So you see up until then, it's still somewhat scaled relatively well. And after that, it was over for us. And this is now the line for the streaming setup, where all measurements that we did were in the range between 5 and 9 seconds. And also the outlier behavior was far better, because in a parallel setup, you might say, okay, outliers, we ignore them, outliers are just statistical noise, but they are not. In a parallel setup, a single outlier can kill the performance. So outliers are really something that you should care about. And this shows somewhat that we have, on this system, in this setup, had a much more stable I/O experience with streaming compared to file I/O. I will skip this slide. This basically compares different backends, compares standard networking techniques against using the custom networks that such systems have. These are recent results that we had on Frontier, which are currently submitted as part of a paper to a conference, so not yet published. Where we tried the same thing on Frontier, going up until full scale this time, actually. Also, one important thing already was we had two technologies that we were testing. So there is, usually when using MPI, if you know about MPI, you usually launch, you say MPI run or srun, and then launch an application. And then within that srun call, all sub-processes know each other. But what we want to do for streaming is we want to launch this code, and we want to launch that code, and then we want to tell them somehow, okay, here, this is the other guy, talk to him. And there is a functionality within a MPI called MPI Open Port, which can do that. The nice thing about it, there is even one or two implementations of it that actually works. And Frontier is actually one of them, so we were able to try that out. The other implementation was by going far more low level via libfabric. And this is again one of the points where we couldn't have predicted which one is better. But at the end, it turned out the MPI implementation gave us the better and more stable results. Basically, MPI requires some more communication and management because of the protocol. So the libfabric backend, theoretically, by being more low level and nearly driver level, allows us to be a bit more fundamental, but with the MPI backend, we simply were able to leverage also the system defaults that were implemented by the vendors of the system MPI, which they know better how to optimize it than we do. So basically, we were able to compare two things without changing too much code, or in this case, without changing any code, especially inside Picon GPU, and leaving the theoretical bandwidth limit, which we see as this dotted line below, far behind us.
This was using
Slingshot. Frontier does not have InfiniBand, but HP Slingshot.
And can it use RDMA?
This is RDMA, yes.
RDMA.
Yeah. So the Slingshot or InfiniBand are names of networks. So this is that brand, and this is this brand, and the data path, let's say, or the RDMA is then not. RDMA is then, so we're talking about remote direct memory access. RDMA is then implemented by these kinds of networks so that you can have fast communication without having unnecessary operating system level caching. So yes, this was using RDMA, but this was going via InfiniBand, and this on Frontier now via Slingshot. Also, one of those cases, we have a new network. How do we deal with it? We didn't need to change code in Picon GPU, but we needed to add a backend for it in ADOS. Yeah, some more performance results. We are going to talk about these in the top row tomorrow. The bottom row, so we have talked mostly about write performance so far. There's also consideration about read performance. Not going far into detail on that one, but basically, especially in ADOS, since it has this log structured output format, you need to think about how do I write data so that it is actually readable. And this is actually was done in this study via streaming, so streaming data out in order to read it back but read it back in a more structured way to basically defragment load balanced data. Another application of streaming, but the more interesting thing now is doing it on our own. We are not going to use RDMA today. We are simply going to use the simple network, or the simple here sockets-based default implementation, because it's sufficient for our purposes. And it's in the Jupyter session we only get one node, and by default the Slingshot network will turn off network capabilities on one node jobs, and I honestly didn't want to bother finding out how to enable all that stuff in Jupyter, so we are now going to use sockets for this. Shouldn't matter, because the thing that matters for us is the workflow, and if you have the workflow set up, then it's a matter of setting up the installation correctly so that the fast backends work.